Thank you, Thomas. Thank you, Elio, for arranging this marvelous conference and inviting me here. I was only too sorry that, thanks to Eurowings, I missed the first 2 days, and that's why my anyway. So today I'm going to tell you about work we've been doing on the concept of order fractionalization, and this is work that really connects me with many collaborators over the last 10-20 years, particularly my longtime collaborator Alexis Felik, who has told you a little bit about this work a few days ago, my current student Aditya Panigrahi, but also this cast of characters who've worked with me over the years. This is a story which really takes us back to work that we first started in the 1990s, and which has come back to haunt us in various ways that I'll come to tell you about. And it really concerns the ways in which a spin can fractionalize. I'm getting a lot of feedback to myself from the, okay, never mind, I'm hearing it twice. Okay, good. So these are, the work is on the archive, the most recent work that announced up there, but also some older work that goes back to this work we did in the 1990s, asking, are heavy fermion insulators gapless? Okay, so this is my outline. How far I'll actually get, I don't know. I may have to skip through some sessions, parts of the talk. I'm going to begin with talking about the motivation. I'm going to then tell you about the concept of fractionalization as a kind of emergent second quantization. Then I'm going to tell you about the Yao-Lee model and how we've been able to combine it in a Kondo lattice to produce a exactly solvable three-dimensional Kondo lattice. And then I'll talk about a wild idea that sort of connects the work that we've done up with the original motivation. So I'll return to the motivation at the end. So this is really a story that goes back a long way. In the 1960s, it was believed that F electrons are entirely localized, and work on samarium hexaboride initially in Siberia and then at the labs led to the conclusion that that's not in fact the case. Here are the valence fluctuations seen in core level spectroscopy in 1965, Weinstein et al. And this was then picked up by the late Ted Jabal, who died just last year in the middle of COVID at the age of 101. And he studied samarium hexaboride and discovered it had a very narrow gap of about 4.6 millivolts, or about 1.1 terahertz in the conductivity. And there are many mysteries about this material which have continued and in fact persist to this day. This particular material really has spanned 50 years of quantum materials, and it's a testament to how our perspectives change with time and how very much more we have still to discover. Okay, these materials today are really the test bed of our exploration of entanglement in quantum materials, and it's my personal belief that just as the birds provided inspiration for Otto Lilienthal and the Wright brothers to develop airplanes, these materials provide us with the inspiration we will need for the next generation of quantum technologies. So over these 50 years, look at all the discoveries that have been made 50 years before Majorana fermions, and yet as our understanding of quantum matter has improved, our conceptual lexicon has evolved, and Kondo insulators have slowly revealed new features. I'm afraid this is going to just fall off. Okay, never mind. Okay. And so look at all the various concepts that have developed along this time. Okay. And so let me just show you some of the early discussions on this material. The late Sir Neville Mott was very instrumental in setting the early tone of the field. The original idea was that there were a lot of valence fluctuations, but he came to the conclusion that in samarium hexaboride, the very small gap was due to hybridization of 4F and 5D bands. But he wasn't entirely sure. He thought it might be a kind of excitonic insulator. And when he extended his discussion to think about cerium aluminium 3, he came to the conclusion that probably this was a Kondo lattice. The word Kondo lattice hadn't been introduced yet, but he suggested that, that you might get a novel form of paramagnetism if the Kondo temperature was higher than the RKKY temperature. This paper was submitted by Neville Mott to Philosophical Magazine, of which he was the chief editor, and one suspects that he may have been the reviewer of the paper. Anyway, it was almost unknown for about 30 or 40 years, this paper. So recently people have realized that he made this suggestion about the Kondo effect. It was, however, picked up by Sebastian Doniak, and he formulated these ideas in what he called the Kondo lattice, a model that had been proposed by Kasuya in 1951, but not considered with antiferromagnetic superexchange until Doniak came along. And he did some beautiful work on this in low dimensions and came to the conclusion that there would be a second order, in other words, a quantum critical point in the phase diagram. And so this was a visionary point of view. It took a long time to figure things out, but it led to this phase diagram that we often show. Now, so despite this qualitative phase diagram, this model has proven extremely resilient against attempts to produce controlled approximations. And part of the problem is that it contains this spin here. And spins are very difficult to express in a second quantized language. And one of the original proposals by Abrakozov was basically a fractionalization proposal for the spin, because the spin in this model comes from wherever it came from. It could be a nuclear moment, hyperfine coupled to the surroundings, or it could just be a Hamiltonian that your advisor gave you to solve using tensor networks. Either way, we know that it actually leads to a large Fermi surface in which the spins count as fermions. And the reason they do this is that they fractionalize. So the more recent motivation that has brought us back to this system has been a number of things. First of all, it looks like samarium hexaboride is a topological insulator. And this led to new experiments. And mysteriously, the group at Cambridge found that they didn't see any oscillations in the resistivity that they were expecting from topological surface states, even though the surface is conducting. But they did see oscillations coming from the bulk in the torque to Haspin-Alphen oscillations, which led them to suggest there might be a bulk Fermi surface in this system, an incredible assertion, because it's a very, very good insulator. And the size of the orbits is larger than any percolating structure of metals could incorporate without driving the system back into a metal. And so this has been very fascinating. And in the meantime, a number of other systems, such as terbium boron 12, and most recently, though not yet published, iron diantimonide, have joined the story as systems with good insulating behavior, but marked quantum oscillations. Another, and so what does this mean? It's led to a lot of discussion. And another example of interesting behavior, which I think is equally fascinating, I don't know how to get rid of the UR screen sharing there, never mind, is uranium ditelluride. This is an almost ferromagnetic superconductor with an upper critical field that's in excess of 80 Tesla, despite the fact it has a 2 Kelvin transition temperature. And another strange thing about it is that in the poorer samples, it shows a marked linear specific heat capacity. In better samples, that linear specific heat capacity becomes smaller, but it has not yet gone to zero. And the weird thing about it is that no one's been able to detect a corresponding thermal conductivity, a point I'll come back to later. And so this is also the case in samarium hexaboride, where there's a linear specific heat and no apparent thermal conductivity. How can it be that an intense density of fermionic excitations does not lead to heat conductivity? At the very least, maybe it's an example of many-body localization. I'm just teasing you. Okay, so these are motivations that have brought us backwards and made us worry that these may be examples of new kinds of three-dimensional spin fractionalization. And so let me remind you that in the Kondo insulator, according to Never-Mott's picture, you basically have a hybridized band structure, but this comes from the fact that the spins have fractionalized as fermions. And so this is the canonical picture of a Kondo insulator. But 25 years ago or further time ago, Alexei Svelik and I started playing with the notion that the spin could equally well be represented in terms of Majorana fermions. Now, these are representations, but from the modern perspective, they are also a statement of a pattern of fractionalization that the spin might undergo. So when you flip a spin, you can think of it as giving two spin-ons, which is the first picture. That's the regular Kondo insulator. But you can also, when you flip a spin, have it break up into two spin-one Majorana fermions. And of course, you all know that the commutator of two Pauli matrices is another Pauli matrix. And so this is just that statement that you can combine two spin-one objects into a single spin-one spin flip. And so we played with this years ago, and it led to the notion of a gapless Majorana band. We had a completely uncontrolled approximation, and after a little bit of fun in the mid-90s, we dropped the topic entirely. But it's come back to haunt us in the context of Samarium hexaboride. Bhaskaran suggested that maybe, even though we had suggested this was a superconductor, perhaps we'd gotten it wrong, and instead it was an insulator with quantum oscillations. And we didn't take his work seriously at first, but then came to the conclusion after exploring many more conservative viewpoints that maybe we should think about it again. And so what I'll be telling you about is a model which actually realizes this Majorana Fermi surface rigorously in a Kondo lattice. And so this has made us think, well, okay, maybe it's not even relevant to some hexaboride, but it must be interesting somewhere. And so that's the topic of the talk. Okay, so before I go on, let me tell you about my take on fractionalization. And actually, as you learn quantum mechanics, you realize that actually field theory itself, the existence of a Fock space, is already a very remarkable statement on the nature of quantum mechanics. So if you think about that, if we take the Schrödinger picture, we have a many-body wave function which evolves on a sheet of the Hilbert space with exactly n particles. And that is reality. Okay? There's no need to go beyond that. It contains everything. And yet, of course, if we want to think in terms of particles, if we want to think in terms of creation and annihilation, and the fact that we'd like to write down an operator for example, the density, which doesn't make reference to the wave function, we're forced, as Jordan and Klein realized many, many years ago, almost 100 years ago, to take a Fock description and rewrite the physical operators in terms of fields. So when we probe the density, we create a particle and we destroy a particle at the same time. And of course, this means that we have to expand the Hilbert space into a Fock space. And this is then the basis of our modern understanding of interacting particles. We can add and subtract particles, but the confinement of the wave function to the physical slice of the Fock space manifests as a gauge symmetry that protects the physics and keeps it on that physical slice. As long as you obey gauge invariance, then everything is good. Okay. So what about fractionalization? Well, fractionalization is the marvelous discovery that physical operators split up into emergent particles. And this works in the case of the spin 1/2 Heisenberg chain, which features the fact that magons break up into spin-ons. It's also a feature of the fractional quantum Hall effect, where electrons fractionalize into fractionally charged anyons with fractional statistics. Okay. And so what's going on there, a very nice model to illustrate this is the Kitaev honeycomb lattice, which we can all solve. You can even solve it using the Jordan-Wigner transformation, which is particularly nice to do as an exercise. And so what happens here, well, the physical Hilbert space is the spin system, and yet the spins fractionalize, the spin flips, the magnons fractionalize into gapless Majoranas and massive visons. A vison is a flux through the hexagon. It costs a certain amount of energy to create it. So when you flip a spin, you create a massless fermion and you create a massive vison. So it's a gapped spin liquid, and you can exactly solve it, and it has wonderful properties. There's an emergent Fock space, and the Hamiltonian then becomes a gauge field with a static Z2 gauge field. So confinement to the physical Hilbert space manifests as an emergent gauge symmetry. So every time we have fractionalization, coming along with it is an emergent gauge field, okay? And you might think that this is a figment of the theorist's imagination, but in fact, it seems to be a feature of the real world, this fractionalization. And so this is the Kitaev model. And presumably, there are many other ground states of quantum matter in which physical objects fractionalize in novel emergent ways. And so I'm particularly interested in cases where the spin fractionalizes, but not as a Dirac fermion. Okay. So, come on, go. All right. Oh, it's this button, wrong button. Okay, so it's an emergent second quantization. Okay, so one of the remarkable aspects of Fock space is the phenomenon of superfluidity, because in a superfluid ground state, the density matrix of the particles factorizes in terms of the superfluid order parameter. This is the phenomenon of off-diagonal long-range order. And in condensed matter physics, we kind of treat superconductors in the same way, but actually we are making a kind of egregious error, which our particle physicist friends always remind us about. So in superconductors, we like to think in terms of a Landau-Ginzburg description, but the order parameter, the boson that forms that, of course, has a subtlety. It's charged and therefore transforms under gauge transformations. And so when you average over the fluctuations of the vector potential, that average goes to zero. Even if you try to apply an external field and then take it away, the averages blow up in your face, and this is known as Elitzer's theorem. So goodbye, Landau-Ginzburg. Okay. However, there is a very beautiful way of solving this problem. It's a problem that was discussed by Dirac in 1955 and later by Hansen and Organis and Sondi. And the idea is that you attach a gauge string to the particles. In this gauge string, the A is the physical vector potential, and E classical is a static field that points out from the point of the charge. And what this operator does is it destroys the particle and adjusts the surrounding fields to accommodate that particle's presence. And this combination, this non-local combination, is actually a neutral object. And in terms of this neutral object, you can now describe an XY model that is causal and local and has all the right properties. And this, in this revision, the psi n is now an order parameter and can condense, okay? And so this is gauged off diagonal long range order. And so this raises an interesting possibility. So when we fractionalize a spin or some other operator, we introduce gauge fields. And so we can't really imagine pairing a particle with one of those fractionalized objects unless we think about the gauge invariance. And so the question we asked some years ago in a paper that received a lot of opposition and is still just an archive preprint, can fractionalized bosons form and develop off-diagonal long-range order, e.g. by binding fractionalized particles to electrons? So once you've got these fractionalized particles, can they pair or do whatever they like to do with other particles? And if they do so, does that mean that you've got a kind of gauged off-diagonal long-range order? Okay. So we've been exploring that possibility, and we've taken advantage of some of the beautiful work that's been done on spin liquids over the last 10, 15 years, beginning with the Kitaev spin liquid. And so we're going to talk about order fractionalization in a solvable Kondo lattice model. Okay. And Alexei already talked about this last week, and I'm going to take you through its key properties in a cartoon fashion. The full glorious details are in the two preprints that I mentioned earlier. Some 11 years ago, Yao and Lee produced a generalization of the Kitaev honeycomb lattice. And this is their model, the Yao-Lee model. They defined it on honeycomb lattice. And curiously, no one took the model to any other lattice. However, in the meantime, there's also been a huge expansion of the Kitaev model to many lattices. Let me just introduce this model to you. Here are orbital degrees of freedom, okay? And they really behave in the same way as the spin degrees of freedom in the Kitaev honeycomb model. So there's an X, Y, and Z bond colored red, green, and blue here. And then there are also these spin operators here, which decorate the bond, but preserve a rotational invariance in the spin space. So you can take this model and you can treat it in exactly the same ways as the Kitaev spin liquid. And when you do so, you discover that the orbital degrees of freedom basically form a valence bond solid, just like they do for the spins in a Kitaev model. Frustration localizes their degrees of freedom, but the Majorana degree of freedom that they might have had were it a Kitaev system fuses with the spins and converts them into spin-ons, not your grandmother's spin-ons, but actually Majorana spin-ons. And this is the representation of the local moment in terms of those spin-1 spin-ons. And it's absolutely rigorous. And what happens in this model is it actually undergoes an Ising phase transition at a finite temperature. It's around 1% of K. And at that transition, the visons, the vortex excitations of the static gauge field, develop a mass. And below that temperature, the fractionalization becomes secure. So here's the vison here, okay? And so at low temperatures, you can now remove the visons, choose a gauge in which the U's are all equal to 1 with some little provisos about how you order I and J. And then you can go ahead treating this as a completely non-interacting problem. You get a 4-band Hamiltonian. Let me say a little bit about this frightening lattice. Why have we chosen this lattice? Well, we didn't choose it, first of all. It was invented by Maria Hermans and Simon Trebst. And they chose it because it's trivalent. It's cubic as well. It actually is a BCC lattice. And at each site on the BCC lattice, here's one corner, here's the center of the cube. There will be another, I think there's a little helix of 4 atoms. And you connect these helices up, and it looks like you've broken the symmetry in the Y direction or Z direction, but actually it's completely cubic. There are helices running in all directions. You just can't visualize it, and you have to play with a model of it to see the remarkable structure. It's perfect cubic symmetry, but it does have a chirality to it. And so here is the Hamiltonian you get when you set the U's to 1, and you can diagonalize it perfectly. And what's most important that Hermans and Trebs discovered is it has a beautiful Majorana Fermi surface. But they did it in the Kitaev model on a hyper octagonal lattice. And we've upgraded it using the work of Yao and Lee to a Yao-Lee model on the hyper octagonal lattice. And the beauty of this is that this is now a spin-on Fermi surface. This is a gapless spin liquid, okay? This is the realization of a dream that has been sought for many years. It's a solvable, 3-dimensional spin liquid with a Fermi surface, and the gauge fields are absolutely static. They commute with the Hamiltonian. So you can get inside it and you can play with it. And so when we discovered this marvelous model, it then led us to say, well, can we couple it to charge? And the way we know how to couple it to charge is to introduce a Kondo exchange. And so that's the idea. This is the gauge invariance of the underlying fluid, okay? And now let's introduce the Kondo coupling. Here's the Kondo coupling. We're now going to allow electrons to hop on this lattice with the nearest neighbor hopping. And they can now hop around and they will now couple to this spin, but this spin is fractionalized like this, okay? So you've got to now plug this in to that formula and then see what happens. So let's do that. And it turns out if you play around with it, the fractionalized operator then has a nice description. It looks like this. And you can think of this as the square of a spin one half boson called little v. And little v looks like this. It's a charge E spin one half spinner. And you can see it comes in with a negative sign here. So it loves to condense. And if you want to explore its properties, you can do conventional Feynman diagrammatics because the fractionalization is rigorous. This is like thinking about a Stoner problem or a Cooper pairing problem. And we first did this in a honeycomb lattice where it turns out there's a threshold for the value of J as a good learning curve. Then we moved to the three-dimensional system and we discovered something rather remarkable. So here's the model, okay? Let's now look for fractionalization and split it up using a Hubbard-Stronovich decomposition, okay? Or you can do diagrammatics, okay? And let's now add in the hopping of the electrons. Here they are, this is plotted out. And the marvelous thing is that the Fermi surface of the electrons with nearest neighbor hopping is exactly the same as the Fermi surface of the Majoranas, provided you don't introduce a chemical potential. So at particle hole symmetry, the Fermi surfaces nest, okay? You're inclined to say, oh, well, that will lead to a particle hole instability, but actually the Majoranas don't know whether they're particles or holes. They have no clue. And so actually it has elements of particle hole. It's a density wave, but it's actually a pair density wave in which the order parameter is a charge E spin one half spinner, okay? And the susceptibility, the pair susceptibility for this, since it involves two Fermi surfaces that are identical, okay? You can think of it as a Piles instability. You can think of it as a Cooper instability. It's a 1e Cooper pair instability has a logarithmic divergence. And this means that for the smallest value of coupling you imagine, the instability will occur when J times chi equals 1. And since chi blows up on you, this means TC2 is exponential in -1 over J, okay? And so we can rigorously say that the moment you turn on pairing, this system develops a charge E condensate. And we can, furthermore, we can construct the gauged operators that give us the off-diagonal long-range order. And in the gauge we're working, those intermediate strings of gauge fields are identically equal to 1. And so we can know that having calculated in this gauge, we have off-diagonal gauged long-range order of this 1e operator. And there are many things I could say more about this. Let me just talk a little bit about the spectrum. So what happens here is that we have in blue the 3 Majorana fermions of the spin, and in red the 4 Majorana fermions of the conduction C. And you see it's like musical chairs in which 3 of them manage to grab a chair and hybridize. They're gapped out, but one gets left behind. And so what you end up with is a Fermi surface of conduction electrons, just as we'd imagined back in the 90s with an uncontrolled mean field theory, okay? It's a neutral Fermi surface, neutral in big inverted commas, okay? And so if you look at the pairing kind of looks like this. You've got this self-consistent order parameter, pairing, hybridizing the Majorana with the conduction electrons, and it leads to the possibility of an electron hopping into the spin liquid and then hopping out. But because that spin liquid is neutral, it hops out as an electron or as a hole. So you can look at the self-energy, and just a few words about that. The self-energy looks like the self-energy of a Kondo insulator, but it has this projection which projects out the gapless fermion. And so this gaps out the scalar component, and so only 3 components of the conduction C can dive into the neutral spin liquid, and the other one just travels along as a neutral partner, okay? So that's what this model has, and there are a lot more details that I don't have time to go into, but maybe one more picture. It's a pair density wave, and so actually, if you look at the sign of the composite order parameter, it alternates from site to site. It also has a D vector. It has features of odd frequency pairing. It satisfies the spot equals -1 acronym. and on the Fermi surface, it's an odd frequency superconductor. So it combines many crazy paradigms: neutral Fermi surfaces, fractionalized order, pair density wave. It's a monster, but it's exactly solvable. Okay, so now I want to come back to the Samarium hexaboride conundrum with a few last remarks on this. And so these are the things that confuse us about this material. It's a system that is electronically insulating, but hosts seemingly gapless bulk excitations. So here is the linear specific heat. It's about 10 to 50 times lanthanum hexaboride, which is a good metal, but this is a good insulator. Here's the optical conductivity. It's an AC-DC system. It's an AC metal, but a DC insulator. And you're left wondering, well, does that actually go down to 0 here? But what if it didn't? Okay. And going on, come on. This gap here is about 2 delta G. You may remember from Ted Jabot's work is about 1.1 terahertz. And look, you don't see the exponential decline of the excitations here. Why not? Okay, there should be a great big pseudo gap here, and it's not there, even at 1.6 Kelvin. Where did it go to? How come the system is insulating so well at 1.6 Kelvin, but there's so much optical conductivity? Is it just, well, what's it due to? Okay. Here is the thermal conductivity, which doesn't show quasiparticles, but in a zero field, but shows a field-induced component. And here are the de Haas van Alphen oscillations, which some groups claimed might come from aluminium impurities, as some of these samples are made from the melt, but actually these samples were made using image furnaces. There's no aluminium there at all. They're also isotopically pure, and just because your lab can't reproduce this data doesn't mean to say it's a fraud. It means it's just hard to get the materials right, and that's been re-established with iron diantimonide and a terbium boron 12. This is real, okay? The bands resemble lanthanum hexaboride. So it's got a bulk linear specific heat. It's an AC-DC metal insulator. It's got a field-dependent thermal conductivity, a bulk de Haas van Alphen with a Lifshitz-Korsavich form, and it's utterly mystifying, okay? And so this is the debate, okay? Is this a topological Kondo insulator, which I was involved with, okay? And are all the other weird things just manifestations of the weirdness of a topological Kondo insulator? Possibly, but on the other hand, I've tried to emphasize that there are a lot of very strange things which then emphasize the possibility of a neutral Fermi surface, and this cast of characters have explored this possibility. But it still raises many, many questions, very many puzzling questions. Okay, for example, if you think that you can get a neutral Fermi liquid, a neutral spin liquid with ring exchange, for example, that connects to the external field and thereby produces de Haas van Alphen oscillations, good for you, okay? But what does that mean about the low frequency electrodynamics of your fluid, okay? And why is the resistivity so robust? If in-gap impurities produce the linear specific heat, why don't they delocalize? Okay, there's been some interesting work by Brian Skinner in which he examines the possibility of metal insulated transitions in topological insulators and comes to the conclusion that you need a much higher concentration of disorder to get a metal. Okay, but still you've got the question, okay, well, but why don't I see thermal conductivity if the fermions are mobile? And last but not least, the really simple thing is, didn't I think that Landau quantization was a semi-classical phenomenon? And weren't we taught that semi-classical systems we can think of classically as responding perhaps to a Lorentz force? And how then can an electron that responds to the Lorentz force not respond to the electric field? Okay. And so this, let me end now with a proposal. I don't have a theory for samarium hexaboride, although we're trying to develop one. This is a proposal to try to develop, as Francis Bacon once said, an intermediate picture. Rather than going to the full-fledged microscopic theory at the beginning, go gradually from the particulars and put together a model that describes some aspect of the experiment that you can then examine with further experiments. So let's try to do that. That requires a little bit of craziness, okay? So here's the craziness. We know that the divergence of the current is 0 in this system because it's a great big insulator. But we also know that there's a magnetization, and the curve of the magnetization is J, and it's a basically DC thing, and it's a huge current running around the edge of this system, okay? And so this suggests that we might have a novel fluid that allows divergence-free circulating currents, but with an insulating longitudinal conductivity. If you'll bear with me for a moment, let me remind you that we divide the conductivity into a longitudinal, which responds to the electric field that couples in the direction of the Q vector, and a transverse, which responds to an electric field which is perpendicular to the Q vector. And normally we assume that at long distances, the longitudinal and the transverse conductivities come together as a single DC conductivity. And if they don't, something weird is going on, because this would lead to sort of singular behavior as a function of Q at low frequencies, okay? But this system kind of makes you say, well, okay, I know this part is gapped, okay? It's been known for 40 years. And this part, well, maybe it's not. Maybe this system is what we, for the want of a better word, is a transverse metal, a metal that responds only to transverse electric fields and is otherwise an insulator. It's the ultimate AC-DC system. And if that were true, how could you test it? Well, the first thing you'd want to do is to extend this picture to lower frequencies, okay? Make a cavity, look for cyclotron fluctuate oscillations, okay? Do things in the megahertz. And if everything is conservative, then what we expect to happen is that this blue line will go straight into 0, okay? And from the gradient of this, you'll pick up the dielectric constant, which must be huge, okay? But maybe it doesn't. And maybe we already know it doesn't, because we've been seeing the Husman-Alfvén oscillations. Lastly, we know that we've got a model, which is a superconductor, but maybe we can slightly disorder it and explain this physics. Maybe with next nearest neighbor hopping, there's a linear coupling to a vector potential. There is actually in this model. And so these neutral particles aren't really neutral at all, okay? And lastly, such a fluid will basically decouple from phonons with long thermal equilibration times. And we know in these systems, it takes sometimes more than an hour to measure the specific heat capacity. Well, draw a resistive circuit for this. That means you've got a CR constant that's 1 hour, a great big thermal resistance in series with your spin liquid, whatever it is, and you've got to take that into account. So probably some of these systems have a good thermal conductivity that the experimentalists have just given up after 1 hour and haven't measured it carefully enough. So you've got to do it much more carefully. And that's it.